Namaste students, welcome back. In our previous video, we have studied about the factors affecting ionization enthalpy. Today, in this video, we will study the variation of ionization enthalpy in our periodic table by keeping the previous video in our mind. First of all, we'll talk about the variation of ionization enthalpy in period. Now, as we move left to right in a period, if we talk in general, so as we move left to right in a period, what happened? Atomic size decreases. Due to the decrease in the atomic size, nuclear force of attraction increases. And due to the increase in the nuclear force of attraction, it becomes difficult for us to remove the loosely bounded electron from the atom, as a result of which ionization enthalpy increases. So if we have to answer generally, then our answer is, as we move left to right in a period, the ionization enthalpy increases. But in our previous video, we have studied different factors which affects the ionization enthalpy. And when we kept those factors in our mind, then there are lots of exceptions in between the periods. Let us take an example of the first period, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Now, as we move from lithium to beryllium, the electronic configuration of lithium is 1s2, 2s1 and it is 2s2. So, as we move from lithium to beryllium, what happened? Atomic size decreases. Due to the decrease in the atomic size, nuclear force of attraction increases. Clear? And in this we have half-filled s orbital, whereas in this we have fully filled s orbital. So fully filled s orbital is more stable as compared to the half-filled orbital. Therefore, it becomes difficult for us to remove the electron from the beryllium. So the answer is, in beryllium, the ionization enthalpy is more as compared to the lithium. The general trend. So as we move from lithium to beryllium, ionization enthalpy increases. Now, as we move from beryllium to boron, the electronic configuration of boron is 2s2 2p1. The electronic configuration of boron is 2s2 2p1. Now, in this we have to remove, as the size of the boron is less than that of the beryllium. Now, if we kept this thing in our mind, so our answer becomes boron, because size is small, so it becomes difficult for us to remove the electron. So the boron should have higher ionization enthalpy than the beryllium. But the first ionization enthalpy of beryllium is greater than that of the boron. Now, what is the reason behind this? Ionization enthalpy decreases. We are dealing with the first ionization enthalpy. Because this is the ground state configuration. So on the basis of the ground state configuration, we are dealing with the first ionization enthalpy. So on moving lithium to beryllium, ionization enthalpy increases regularly. But on moving beryllium to boron, instead of increasing, it decreases. Now, why it decreases? There are two factors which explain this phenomena. First one, that in this case, the outermost orbital is s orbital and it is fully filled. That's why it is stable. In this, the outermost electron is present in the p orbital, which is partially filled. So, in boron, we have to remove electron from a partially filled orbital, whereas in beryllium, we have to remove the electron from the fully filled orbital. And we know that fully filled orbital are more stable as compared to the partially filled orbital. Therefore, it becomes difficult for us to remove the electron from the s orbital as compared to the p orbital. And second phenomena which can explain here, that is penetration effect. We have studied penetration effect, that if we have same shells, then the different subshells experience different force of attraction by the nucleus, and in the same cell the S subshell experience the most nuclear force of attraction. So here it is 2s and here it is 2p. So both belongs to second shell, and because 2s is near to that of the nucleus, therefore the force of attraction experienced by the 2s is greater than that of the 2p. As a result of which penetration effect is more in 2s as compared to 2p. Therefore, it becomes difficult for us to remove the electron from 2s as compared to 2p. Therefore, ionization enthalpy decreases. Now next, when we move from boron to carbon, here the configuration is 2s to 2p2. In both the case, we have to remove the electron from the 2p subshell. So there is no role of the subshell, there is a role of only the nuclear force of attraction, and in carbon the nuclear force of attraction is more than that of the boron. Therefore, ionization enthalpy, what happened? Ionization enthalpy increases. Ionization enthalpy increases. Now next, if I talk about the nitrogen, its electronic configuration is 2s to 2p3. So when we move from carbon to nitrogen, what happened? Both the factors favors the greater ionization enthalpy of the nitrogen. As we move from carbon to nitrogen, atomic size decreases, as a result of which ionization enthalpy increases. And as we move from carbon to nitrogen, the stability of the configuration increases. In this, we have half-filled p orbital, which is stable as compared to the partially filled orbital. That's why this one is more stable, as a result of which what happened? Ionization enthalpy increases. Now, as we move from nitrogen to oxygen, ionization enthalpy, that is the first ionization enthalpy decreases. Now, why first ionization enthalpy decreases? Because of the configuration. In nitrogen, we have stable configuration. Means when we remove one electron from the nitrogen, the configuration becomes 2s to 2p2, which is less stable. But when we remove electron from the oxygen, then its configuration becomes 2s to 2p3, which is more stable. So because of this reason, ionization enthalpy decreases as we move from nitrogen to oxygen. So due to stable configuration, the first ionization enthalpy of nitrogen is greater than that of the oxygen. And as we move from oxygen to fluorine, what happened? Ionization enthalpy again increases. Why ionization enthalpy increases? Because in fluorine, the electronic configuration is 2s to 2p5. So the electron is present in p orbital. So there is no role of the subshell. There is a role of only atomic size. So on moving oxygen to fluorine, atomic size decreases, as a result of which ionization enthalpy increases. And when we move from fluorine to neon, ionization enthalpy increases because in neon the electronic configuration is more stable. So it becomes very difficult for us to remove the electron from the neon. So in this way, the ionization enthalpy varies in a period. So in general, ionization enthalpy, yes, increases on moving left to right, but it is not necessary that at each element ionization enthalpy increases, because other factors also influence ionization enthalpy. And if we talk about the variation in group, variation group is simple. On moving down the group, what happened? Shells increases. Due to the increase in the shells, ionization enthalpy increases. Due to the increase in the shells, the distance from the nucleus to the valence electron increases, as a result of which it becomes easy for us to remove the electron from the outermost cell, as a result of which ionization enthalpy decreases. So on moving down the group, ionization enthalpy decreases due to the increase in the number of the shells. So this is all about the variation of the ionization enthalpy. Now we will do one question based on the ionization enthalpy so that the concept becomes more clear to you. So here is the question. some of the electronic configuration are given to us, and we have to arrange these in the increasing order of ionization enthalpy. We have to arrange these electronic configuration in the increasing order of ionization enthalpy. Now, if we look the electronic configuration, in first two electronic configuration, we have three shells. Means here is the nucleus, first shell, second shell, and third shell. Means in first and second configuration, the outermost electron is at maximum distance from the nucleus. So obviously it becomes easy for us to remove the electron from the third shell as compared to the second and first shell. So obviously the lowest ionization enthalpy is of either 1 or of 2. Now if we look 1 or 2, if we observe 1 or 2, in first the s orbital is fully filled, and in second the s orbital is half filled. In first, if we remove electron from the s orbital, it becomes half filled. And in second, if I remove electron from the s orbital, the configuration get converted into the octet configuration, that is 1s2, 2s2, 2p6. It means by removing electron from the second orbital, I convert this less stable configuration to more stable configuration. So it becomes easy for me to remove the electron from the second configuration. So the lowest ionization energy is of the second. Now obviously the second one is first. Now out of third, fourth and fifth, in third, fourth and fifth, the outermost shell is 2p, outermost subshell is 2p. In this I have 2p4, in this I have 2p5, and in this I have 2p6. Now if I remove one electron from this, it becomes 2p3, that is a more stable. So it release the electron more easily as compared to these two, because after removing one electron, it get converted into 1s2, 2s2, 2p3, and therefore its ionization enthalpy is less than that of the 4 and 5. Now out of 4 and 5, the fifth one is stable configuration. So it becomes difficult for us to remove the electron from the stable configuration and easy to remove the electron from this configuration. So next is 4 and the next one is 5th. So the order of ionization enthalpy is second, the least, then first, then third, then fourth, and the fifth one has the greatest ionization enthalpy. So when you solve this question, you have to write the explanations also. You have to write the explanation also, that why the ionization enthalpy of second is least, then why in second number we have first configuration, in third number we have third configuration. So all the explanation you have to write. So in this way you can solve the conceptual questions which are based on ionization enthalpy. So students, that's all for today. I'll see you in my next video with a new atomic property.